Okay, here we are, 3.11, related rates. Set up and solve related rate problems. So example 1, an oil rig springs a leak in column C's and the oil spreads in a circular patch around the rig. If the radius of the oil patch increases at a rate of 30 meters per hour, how fast is the area of the patch increase when the patch has a radius of 100 meters? So what we want to find is what it says here, how fast is the area of the patch increasing. We're going to call that dA dt, which is the speed at which the area is increasing. Okay, what we're given is 30 meters per hour, which is the rate at which the radius is changing. We want to know when this happens if the radius equals 100. So the area of the space, of course, is related to a circle, which is pi r squared. We're going to go ahead and take the derivative with this with respect to t. Okay, and I don't see a variable t involved here, so I'm assuming that a is involved. With a can change based on t, so the derivative of a with respect to t would be dA dt. The derivative of the following would be 2 pi r times the rate at which r changes with respect to t. So I've just done implicit differentiation on both sides now, and what I'm going to do is I'm going to use what I know. So dA dt is going to be equal to 2 pi times the radius at the time that I want, which was 100, times the rate at which the radius was changing, which is 30 meters per hour. When we do a simple calculation here and simplify, it looks like 2 times 300 times 100 is 6,000 times pi meters. Now this 100 was meters as well, so that's meters squared per hour, which, if we go with an approximate answer, would be about 18,849.556 meters squared per hour. Obviously useful to an environmentalist of some sort, or some kind of environmental control or hazmat type team. All right, let's move on to the next example. Okay, an observer stands 200 meters from the launch site of a hot air balloon. The balloon rises vertically at a constant rate. Okay, so we're given this. Let's say dy dt. Right, dy dt would be our vertical rate of change, which is 4 meters per second. And when this happens, well, when this happens is at time 30 seconds, but we don't really want that. We want what the height will be at 30 seconds, which would be 30 seconds times 4 meters per second. 30 seconds times 4 meters per second, which would be 120 meters. Okay, so what do we want? We want the rate at which the angle changes. The rate at which the angle changes is d theta dt. That's what we're searching for. So let's write in an equation. All right, if this is 120, we'll use that in a couple minutes here. But the equation for this would involve the opposite side and the adjacent side. So I'm going to say the tangent of theta equals y of t over this constant 200. And I'm going to differentiate that with respect to t. Okay, but before I do so, I'm going to do a little bit of manipulation to make it a tad easier on me. So I'm going to just say theta equals the inverse tangent of y of t over 200. Okay, so let's differentiate. What that will be is d theta dt. And remember, arctangent or inverse tangent is 1 over x squared plus 1. So it'll be 1 over y of t over 200 squared plus 1. But don't forget we have a chain rule involved, so we're going to multiply by the derivative of the inside here, which would be 1 over 200. And we also want to multiply that by dy dt. Alright, so that's what chain rule would be. Chain rule comes into play there, and now we go ahead and we're going to evaluate what we know. Right, so d theta dt, or the change in the angle with respect to time, when the balloon was released 30 seconds prior, right, this would basically just be y of 3, and this would be dy dt at what we know to be 4 meters per second. So we said y of 3 was 120, so 120 over 200 plus 1 times 1 over 200 times 4. Okay, we can do some reducing. So d theta dt would equal 1 over this, I'm going to put this as 25 over 25. Okay, this would actually reduce here. Oops, we can't forget to square that. This would reduce to 3/5. So 3/5 squared times, and we're going to reduce this to 1 over 50. So let's do a little bit more here. D theta dt would equal 1 over this value here. When I square it, will be 9 over 25. So I would get, what is that, 34. 34 over 25 times 1 over 50. And so therefore d theta dt, if I take 1 over this, it'd be the same as multiplying by its reciprocal. So it'd be 25 over 34 times 1 over 50. We get a little bit of reduction here. That would make that a 2. Therefore, we get d theta dt equal to 1 over 68 radians per second. If we were to approximate that, that would be approximately 0.0147 radians per second. All right. So that's the change in the angle based on that increase in height at 4 meters per second and a distance from the release point of 200 meters. All right, example 3. Okay, so sand falls from an overhead bin accumulating in a conical pile or a cone-shaped pile with a radius that is always 3 times the height. Okay, so let's recall this then. Radius equals 3 times height. Let's look at what we're given. If the sand falls from the bin at a rate of 120 cubic feet per minute, how fast is the height of the pile changing when the pile is 10 feet high? Okay, so I've laid out what we need to find, what we're given, and when it would happen. So the equation for the volume of a cone is given here. What we're going to want to do is most likely just to get this in terms of one variable, which would make things a lot easier, especially since we're trying to find the change in height with respect to time. So before I go ahead and differentiate, what I'm going to do first is I'm going to rewrite the following equation using this. Right, I'm going to do a substitution for r and call it 3h. So this would be 1/3 pi times 3h, that's the same as the radius squared, times h. Okay, and then we're going to go ahead and differentiate this. So d dt. So this would be dv dt, which we know. This would be 1/3, oops, I'm sorry. Let me erase. Oh, that's not the eraser, great. Okay, This might be easier. Hold on a second. Okay, so I went back and just expanded this second one, or simplified it, right? Expanded, then simplified, and now it's going to be much easier to take the derivative. So I would have dv dt, the change in volume with respect to the time, would be equal to, h is the variable, so I'll get 9 pi h squared. Don't forget that you do have to use the chain rule here, and also take the derivative of the height with respect to time implicitly. And now we're going to plug in what we know. We know that the change in volume with respect to time was 120. We know that the height at the time that we were looking for that change in height was 10. And now we can pretty easily solve for the change in height with respect to time. So I'm going to take 120 and I'm going to divide it by 900 pi, and that will be dh dt. I got the 900 pi by taking 9 times 10 times pi. This reduces down a ways. Let's see, what does it reduce down to? 120 over 900 goes to 2 over 15 pi, and that'll be feet. Right, this is the rate for the height, feet per minute. This would be the exact answer. The approximate answer for the change in height with respect to time would be approximately 0.0424 feet per minute. Alright, example 4. Assuming that a soap bubble retains its spherical shape as it expands, how fast is the radius increasing? So dr dt, when its radius is 2 inches, if air is blown into it at a rate of 4 cubic inches per second. So this is dv dt. dv dt. Looks like they were nice enough. We were nice enough to give you the formula for the volume of a sphere, which is 4/3 pi r cubed. We don't need to do any conversions like we did on the last one, so we're just going to take the derivative with respect to time. So that means dv dt will equal, we're going to use the power rule, bring that 3 down in front, that'd be 4 pi r squared. Alright, so now we get to that point. Without forgetting, I almost did, you also have to take the derivative of r with respect to time. So we get 4 pi r squared dr dt. We know dv dt was 4 inches, so this was 4. We got 4 pi r squared times dr dt. We know that r equals 2 at the time we want to know the change. And so therefore we can take 4 and divide by 8 pi, and that'll be dr dt. Let's reduce, that'd be 1 over 2 pi inches per, what were we, second? Okay, and an approximate value for that. Oh goodness, what did I do wrong here? I forgot to square, that's right. Boy, oh boy. Alright, so let's change this real quick. From an 8 then to a 16. That makes this 1 over 4 pi, which makes this approximately 0.0795 inches per second. Okay, either of these two answers would be acceptable. There's an approximate answer. Here's an exact answer. And I believe that's it for today. A couple of tips here when solving these types of related rate problems is read the problem first, draw a diagram, label the diagram, assign some variables, determine what you want to find, what's given, and when it happens. Write an equation relating those quantities. If necessary, rid yourself of unwanted variables. And you got to know some geometry. Simplify before you differentiate. That is a big one. And then find the rate of change. You got it. So get after it, and we'll see you next time.